So we ended the week talking about field lines, or electric field lines, and how they looked with 2-point charges. So a positive and a negative. And we said that if I had two fields, or 2-point charges, the positive charges radiate, or the fields radiate away from, and the negative, the fields radiate into. And we said how these two things would interact, as far as the field lines connecting, and that the number of field lines are proportional to the charges. So these two charges would be a +1 and a -1, then this would be a fair drawing. And so we have our smooth lines, and that's what our field lines would look like-ish, if I'd been a little neater. So we can do more than just 2-point charges. When we get into circuits, which is coming up here real quick, we'll look at how fields behave in between charged plates, or how do we create current. And to begin with, we need to understand how the electric fields behave between two plates. So my plates here I have positively charged, and ask yourself what I would need to do to create that positive charge. And over here, I have a buildup of negative charge. So in keeping with our rules, going from positive into negative, if I draw my field lines, you see, I would just come straight across here. Boom. Straight across. Cool. That's what my field lines look like. And what we'll see in class, and what a couple of you already saw in lab, is that as I come away from here, I will measure certain voltages, and I'll notice my equipotential lines will look something like this. So my field lines are perpendicular to these, but we're going to get into more detail on that later. What I want you to see from this is how the field lines work between two parallel plates, and again with my well-drawn lines, these are indeed parallel, pretend. What happens if I put a little charge guy here in this field? Well, if it's a positive charge, where do you think it's going to go? Do you think it would go to the right, or do you think it would go to the left? Hopefully you said it would go to the right, and that kind of makes sense, or hopefully it does, because it would be repulsed by the positive charge, and so it would want to go in this direction. So it would go in the direction of the field lines. It would be accelerated in the direction of the negative plates. But what happens if I put, say, a negative charge here? Is it also going to go in the direction of the field lines, or do you think it would want to go towards the positive? And hopefully your intuition now is that it would be attracted towards all of this positive charge and not towards the negative. So it would be accelerated, or rather decelerated this way, because it would be fighting against the field. And the way we can express that in terms of our fields, we have the electric field equals K, Q, we'll use big Q, the book does, Q over R squared. So that function of R squared, or that distance dependence, is still true, just as it was with Coulomb's law. But now we can look at a field with these guys specific to one charge. So I can isolate this negative charge, and so long as I know its strength, I can figure out at some point away from this negative charge what that electric field strength is. And I can do the same here. And that end result gives us something like an answer in newtons per coulomb. So then that gives me an idea if I place a charge, or if I want to know what force is on something in a field at a particular point, then so long as I know that charge, I can turn this into a force. Okay, so let's see what those units look like. my electric field equals K, which is 9 times 10 to the 9th. Okay, so I'm shortcutting it. Newtons meters squared per coulomb squared times my charge, which has units of coulombs, over my distance, which is going to be in meters squared. So that cancels that out, that cancels out, and you see that I end up with that it's a function of force over charge. That's all an electric field is. That's part of the reason I said we've done all this work to figure out what happens in all these fancy-dancy geometric configurations. Now we get down to the electric field, and everything is the same. I can now calculate the electric field for this charge and the electric field for this charge, and I can find out what the net electric field is. I can figure out where it'll be 0. Oh, that's a fun one. We're going to do that here quick. I can come up with all sorts of great information. Specific to these plates, then, I can look and I can decide, is this guy going to be speeding up or slowing down? Is this guy going to be speeding up or slowing down? And what direction are they going? So there's all sorts of handy information that we can get just from knowing what these electric fields look like. So the one thing for some of you who haven't had physics before, you see in your homework, you'll have something like this. You'll have a charge, or some mass, or whatever they want to call it, and they'll say, here's its velocity vector. Remember, all vectors give you direction and magnitude. So we could call this a magnitude of 10 meters per second. And if I put it on a line, then it also has its direction. Okay? Acceleration is a change in velocity. So if my velocity vector goes out this way and it gets a little bit smaller, and it gets a little bit smaller, it gets a little bit, I don't know why I'm making the arrowhead smaller. There we go. Make it obviously decreasing. So the magnitude is slowly decreasing. That means that I have some sort of force slowing it down, decelerating it, or accelerating it in the opposite direction of its motion. We call that accelerating it in a negative direction relative to its motion. So if this was an electron in this field, if I put an electron, a negative electron, in this particular field and I put it here, it's going to be attracted this way, but whatever velocity it came in with, it's going to be decreasing going against the electric field. Pretty cool. If I put a positive charge, let's put a positive charge, go a plus Q, in that same field, we'd see velocity vectors that would go something like this, because it's being accelerated. So its velocity is increasing as it's going towards the negative charge. It wants to go there. The negative charge also wants to go towards the positive charge. It's attracted that way, but it's got to fight against all this the field strength going this way. I guess, and you could kind of think of it like a river. This one wants to swim upriver because it's more attracted to this positive charge than it is to this crocodile-filled side of the bank. So it's going to swim upriver, but it's still fighting against the flow to get there. Here we have yummy hamburgers. Here we have crocodiles that don't like you. Now for this positive charge here, it wants to accelerate this direction, and it's lucky because for it, these aren't crocodiles, these are the hamburgers, and it's accelerating towards them. Or make that tofu, or whatever. Float your boat. So that is the basic overview of what we're going to get into, and as I hinted at, the next video we're going to do some math. How fun.